Our group is presenting The Mechanics of Fracture and Failure in Graphene by Maxim Srama, Razan Suleiman, David Tiff, James Vo, and Andrew Weber. To understand the properties of graphene better, I will present the complexity of atomic structure. The atomic structure of graphene consists of a single layer of carbon atoms arranged in a 2D hexagonal lattice. The carbon-to-carbon molecular bonds in this lattice are incredibly strong, with a bond length of about 0.142 nanometers. Each carbon atom undergoes sp2 hybridization. These create strong sigma bonds with a neighboring carbon atom. This results in a trigonal planar geometry with 120-degree angles between bonds. All of these properties of the atomic structure significantly contribute to its properties. Graphene is incredibly strong and conductive. Atomic scale defects can significantly alter its properties. Two common types are vacancies and Stonewall's defects. Vacancies occur when carbon atoms are missing, disrupting the lattice and leaving behind unpaired electrons. This weakens mechanical strength, introduces local magnetism, and reduces electrical conductivity. It also increases chemical reactivity at those sites. Stonewall's defects form when a carbon-to-carbon bond rotates 90 degrees, converting four hexagons into two pentagons and two heptagons. These create local strain and slightly change electronic and mechanical behavior. Interestingly, they can enhance chemical reactivity, which is useful in functionalization processes for sensors or catalysis. Both types of defects serve as reminders that even at the atomic level, imperfections can have a significant macroscopic impact. Graphene's electronic properties are deeply tied to its band structure. In its Brillouin zone, the conduction and valence bands meet at special points called Dirac points, labeled K and K' in the diagram. At these points, the energy-momentum relationship is linear, forming cone-like structures known as Dirac cones. This gives rise to semimetallic behavior. Electrons in graphene behave like massless Dirac fermions, enabling extremely high electric mobility. However, graphene's zero bandgap limits its use in traditional digital logic applications. To address this, researchers explore methods such as doping, applying strain, or using narrow graphene nanoribbons to open up a bandgap. These strategies expand graphene's potential into areas like transistors, flexible electronics, sensors, and even radio frequency devices.
Graphene is a unique 2D material that is comprised of a single layer of pure carbon atoms. It was first derived and researched in 2004 in a laboratory at the University of Manchester in England, where a single layer of graphene was isolated from a chunk of graphite using Scotch tape. Graphene is sometimes referred to as a miracle material due to its high potential. It is claimed that graphene is stronger than steel and lighter than aluminum at equivalent quantities, all while possessing high thermal and high electrical conductivity. There are different categories of graphene. Graphene monolayers are created either using the Scotch tape method or chemical vapor deposition. Graphene oxides are created through chemical oxidation processes, and graphene nanoplatelets are created by breaking down graphite, either through mechanical or chemical means. It is important to note that as layers of graphene are stacked on top of each other, the material loses its strength and flexibility properties. There are a couple of ways that graphene can be extracted. The more common methods that are used include mechanical exfoliation, chemical vapor deposition, and chemical reduction. Mechanical exfoliation of graphene, which as mentioned earlier, can include using Scotch tape to separate single layers of graphene from a larger chunk of graphite. Chemical vapor deposition involves the growth of carbon atoms that nucleate onto a metal substance after hydrocarbon atoms decompose. Chemical reduction is a process where solvents and surfactants like water or oil are combined to suspend single layers of graphite, or rather, to suspend single layers of graphite oxide sheets. The image provided shows a grading system of each preparation method where G equals graphene quality, C is the cost of production, S is the scalability, P is the purity of the product, and Y is the yield. With the many ways to prepare graphene, it also means that there are many different products that can come as a result. It also leaves a greater room for defects to occur in the final product. Looking at graphene at its purest form without any defects, as a monolayer, it is considered as the strongest material to ever be tested, boasting an intrinsic strength of 130 gigapascal. The fracture stress of a perfectly flat layer was found to be 97.5 gigapascal, while a layer with wrinkles had a fracture strength of 60 gigapascal. It was also found that the polycrystalline graphene had a fracture toughness that was 20 to 35% greater than the graphene of pristine crystal structure. However, it is important to note that even though single layers of graphene are incredibly strong and resilient, as more layers are stacked up on top of each other, the material becomes extremely brittle and fractures with little to no deformation.
On this slide, we're looking at the fracture mechanics and failure behavior of graphene. Graphene exhibits a brittle fracture, meaning it breaks suddenly without significant deformation. While its theoretical strength is extremely high, around 100 gigapascals, failure often occurs at much lower stresses due to imperfections like grain boundaries or missing atoms. Crack propagation in graphene follows energy balance principles, and it looks at how different failure behaviors are observed depending on structural details. For example, crack tip blunting and the orientation of grain boundaries can significantly influence how and where graphene fractures. Looking at the image on the right, we can see a simulated crack propagation through a graphene sheet and a stress strain curve showing brittle failure. The plots labeled E and F compare simulation data with theoretical predictions, showing that real-world graphene fractures at lower stresses than expected due to these defects. Fracture is typically initiated by very small flaws, about 1.4 nanometers, most likely due to defects in the atomic structure, like pentagon-heptagon pairings, or what we call 5 to 7 defects. These defects are usually the first to break or show failure within the structure. As strain increases, failure tends to localize at grain boundaries. As shown here in the figure, the grain boundaries in the red triangles can retain higher intrinsic strengths, reaching up to about 93 gigapascals. But as we increase the inflection angle, or the amount of bending at the grain boundary, seen on the x-axis here, the intrinsic strength drops off sharply. The dominant failure mechanism here is known as the Stonewall's bond rotation, which occurs at the boundary and compromises the material's structural integrity. Flat grain boundaries are stronger, while more curved boundaries are weaker and more prone to failure. To reduce failure in graphene, we look at how loading, orientation, and bonding affects its structural integrity. First, higher strength configurations occur when the applied load isn't perfectly aligned with the graphene's normal vector. That misalignment can actually help the material handle more stress before failing. Second, choosing plane orientations that are less prone to buckling, such as glide planes, can significantly improve stability under stress. This is especially useful in layered or composite structures. And third, strong interfacial bonding, particularly between iron and carbon, plays a huge role. When iron-carbon bonds are strong and strain is minimized at the interface, adhesion improves and failure becomes less likely. On the right, you can see visual representation of the graphene layers and how atomic orientation affects structural behavior.
This slide illustrates how graphene's atomic arrangement influences its mechanical behavior. Within graphene's hexagonal lattice, we define two key directions, zigzag and armchair. As shown in the diagrams, the zigzag direction runs along the carbon-to-carbon bonds, while the armchair direction cuts across the hexagons. Graphene exhibits high tensile strength in both directions due to the strength of the carbon-to-carbon bonds, however, there are important differences. The armchair direction is stiffer, meaning that it has a higher Young's modulus. Conversely, the zigzag direction can stretch further before it breaks, exhibiting a higher fracture strain. Interestingly, cracks propagate more easily along the armchair direction. This means that, despite being stiffer, the armchair direction is the weaker direction from a fracture perspective. Here's a breakdown of 4 different materials derived from or related to graphene. First, we have monolayer graphene, which is just a single layer of the hexagonal lattice. It has excellent properties as we've already covered. We also talked about the defects of graphene, which prevent large sheets to be made as the defects become more common as its size increases. Next is carbon nanotubes, perhaps the most famous form, which has rolls of single or multiple layers of graphene. This retains the impressive properties of graphene and increases applications. Carbon nanotubes are still a complex and expensive to produce form of graphene and has issues scaling the production. A relatively newer research area of graphene is graphene nanoplatelets. These are composed of single, few, and multiple layers of graphene. They have a much lower production cost compared to other forms of graphene and are already scaled for mass production. When using composites, care must be taken to avoid agglomeration, which is clumping up of the nanoplatelets. The trade-off with nanoplatelets is that compared to carbon nanotubes and monolayer graphene, it does have inferior properties. Lastly, we have the best known form that we see in our lives, graphite, which is most commonly found in pencils. This is simply multiple layers, at least 10, of graphene stacked on top of each other. It is a very cheap material and used for its lubricating properties due to the weak van der Waals forces holding the layers together. Graphene nanoplatelets have started to be researched in composites lately, and their main use has been in ceramics. Common ceramics they are used with is alumina and silicon nitride. The graphene nanoplatelets have three main toughening mechanisms. These are crack deflection, crack bridging, and crack branching. Crack deflection helps redirect the crack in the composite material to increase the path length, which in turn increases the energy required by dissipating it throughout the material. Crack bridging helps prevent the crack from opening up by bridging the gap and pulling both sides together. Lastly, crack branching splits the cracks up, which creates multiple smaller fractures instead of one large fracture, which helps the entire material absorb the energy.
Graphene is a remarkable material with many everyday applications, and today we'll highlight three key areas where it's making an impact. First, in electronics, graphene's excellent electrical conductivity makes it useful for touchscreens and other smart devices with flexible displays, improving efficiency and durability. Next, in automotive and aerospace, graphene is being used for fuel efficiency, energy storage, and battery technology. Its lightweight and strong properties make it ideal for vehicles and even space exploration. This material is also currently being tested to see if aircraft durability can be improved while reducing the aircraft weight. Finally, in medicine, graphene's unique properties are opening doors for revolutionary treatments, from nerve cell regeneration to early disease detection, and even cancer treatment. Because of its antibacterial nature, it is showing optimistic results in the medical field. These are just some of the many examples where graphene is used. As research continues, graphene's potential across industries is rapidly expanding. Now that we looked at everyday applications of graphene, let's take a quick look at the reliability of graphene-based devices, which is essential for real-world use in things like flexible electronics, sensors, and energy storage, as previously discussed. Even though graphene is strong and conductive, it still faces challenges under long-term use. Some common failure mechanisms include mechanical fatigue, where repeated bending leads to microcracks, delamination, where graphene peels away from its substrate, electromigration, where atoms shift under high current, and environmental degradation from moisture, oxygen, or UV exposure. Several factors influence reliability, like the quality of adhesion to the substrate, defect density in the graphene, how well it's encapsulated, and the operating conditions like temperature or load. Looking ahead, solutions like self-healing materials, better encapsulation, and AI-based failure prediction are helping make graphene more robust for long-term use. Now let's discuss the environmental side of graphene. First, the way it's made can be an issue. Methods of making graphene can create harmful waste to the environment and use a lot of energy, which involves other harsh chemicals that creates toxic waste. That's something that we as engineers and as society need to keep an eye on as production scales up. There's also concern about how graphene affects the environment after it is being used. For example, graphene oxide can be harmful to aquatic life and it doesn't break down easily, which raises concerns and questions about long-term effects. On the other hand, graphene has a lot of green potential. It can make batteries and solar panels more efficient, and researchers are working on eco-friendly ways to make it, like using plant-based materials. The bottom line is, graphene is exciting, but we need to keep developing safe and sustainable ways to produce and use it. This requires future work in assessments and testing.